Good morning, students. This is the second set of PowerPoint-based notes for Section 5 of our textbook. Previously, we had the periodic table and overview, and that covered Section 5.1. Today, we're going to cover Section 5.2 and 5.3, and even some parts of Chapter 6. So we call this Groups, Trends, and Ions. Previously, we learned to divide the periodic table by using the diagonal stair-step line, where most of the elements to the left of that line are said to be metals, and most of the elements to the right of that line are said to be non-metals, and perhaps a few semi-metals or metalloids sprinkled right around the stair-step line. But now we're going to divide it in a more practical way, up and down, left and right. So in a periodic table, the columns which move up and down are called groups or families, while the rows that move left to right are termed periods, and of course this is how the periodic table gets its name. Now when we're focusing on the groups, initially we're going to look at what is called the representative elements, which are highlighted here. These are all the columns which in the US system have a capital A as part of their name, and they are given their name because they represent. They display a wide range of physical chemical properties. In the representative elements, we have solids, liquids, and gases, positively charged cations and negatively charged anions, things that are relatively large atomic radii and some that are smaller, and so on and so forth. Now, in addition to the representative elements, there are the transition metals shown in blue, the D block, and the intertransition metals shown in the bottom in green, the F block. These are elements that tend to have capital B from the US system as part of their names, and they have more complex electron configurations, and we won't consider them at this time. But later on, when we're talking about how to name ionic and covalent compounds, these areas of the periodic table will become more interesting. So our first group we're going to look at is called the alkali metals. The alkali metals is group 1A except hydrogen, and you can find this information on page 138 in your textbook. The alkali metals are group 1A. Here they're shown in orange. They are the first column of the periodic table. The alkali metals include lithium, sodium, potassium, rubidium, cesium, and francium, and they are highly reactive. They all have one dramatic, obvious property in common. You drop them in water, they explode. Highly reactive. Next to them we have the alkaline earth metals, group 2A, similar sounding. And the alkali earth metals are here shown in purple, group 2A. And they include beryllium, magnesium, calcium, strontium, barium, and radium. Like group 1A, they are cations, with the differences being in group 2A, they tend to be +2. We'll now skip to the opposite side of the periodic table. On the other side of the stair-step line, we're going to have group 6A, the chalcogens. Group 6A is mostly shown here in green. It includes oxygen, sulfur, selenium, tellurium, and polonium. These are anions with an overall negative charge -1. Next to the chalcogens, we have the halogens in group 7A. These are the most reactive. Here they're shown in orange. They include fluorine, chlorine, bromine, iodine, and astatine, and they are highly reactive. Finally, a group that's not very reactive at all. They're often called the noble gases. The implication is that they're upper class and too good for the rest of us. This is group 8A in the US system, and these are the least reactive. In fact, we describe them as being inert. This is the column shown in red at the end. It includes helium, neon, argon, krypton, xenon, and radon, and every one of them is a gas. Now, elements can be sorted into noble gases, representative elements, transition metals, or intertransition metals based upon their electron configuration, as previously taught, and you can see this emphasized in your textbook in the chart on page 138. Now what we're going to do is we're going to look at the way that certain properties tend to change in the periodic table as we go left to right or as we go up and down. And the changes in these properties, which we call trends, periodic trends, they are based upon changes in the electron configuration of those elements. So looking at page 144 of your text, we're now looking at periodic trends, and we're going to review several of them. Our first trend is the atomic radius. The atomic radius is simply a way of estimating the size of the atoms. It's from the center of the nucleus to the very outer edge of the atom shells. Here we have a picture of a periodic table where we have circles representing different elements in terms of their size. And so the metals are shown in a kind of blue color, and the semi-metals that cluster around the stair-step line are shown in gold. And then in gray, to the far right, we have the non-metals. Now the trend for these items is that the radius will increase within a group. That is, if you go from top to bottom, as the atomic number increases, the size of the atom also increases. And that makes sense because as you're increasing the atomic number, you're increasing all the number of all the particles involved, and the number of shells involved, and so of course it would get bigger as you go down a group. At the same time, however, the atomic radius decreases within a period. That is, as you go to left to right, it gets smaller. Now that's interesting because, of course, as you're going from left to right, the atomic number is increasing that way as well. And yet within the period, the radius gets smaller. What's going on? What's going on is that ions are coming into play. Atoms or molecules exist that tend to become negative or positively charged. And the reason why they're either negative or positively charged is that their number of electrons doesn't match the number of protons in the nucleus. Now, you don't make atoms by changing protons. The amount of energy necessary to move protons and neutrons out of the nucleus doesn't happen under everyday circumstances. But you can easily gain or lose electrons. And so some atoms tend to gain and some tend to lose, which means some tend to become positive and some tend to become negative. Ions, once they're formed, those with opposite charges will readily form what are called ionic compounds. A classic example is sodium chloride. Here in the illustration, the smaller gold circles represent sodium atoms, which are positively charged, Na+, and the larger green circles represent chlorine atoms, which have become negatively charged and are referred to as chloride ions. And you can see that the gold and the green automatically arrange themselves into a repeating matrix that leads to a structure kind of like a cube. And this is why the crystals of this ionic compound, sodium chloride, sometimes called table salt, if you look at them carefully, they are cube-shaped because that's the way the ions are held together. How do we find ions with the periodic table? Well, there's a clear trend. We find positively charged ions called cations on the left side of the periodic table. So group 1A, as you see, lithium, sodium, potassium, rubidium, cesium, francium, those all tend to be +1. And next to it, group 2A, why beryllium, magnesium, calcium, strontium, barium, and radium, they all tend to be 2+. And the same thing is true for group 3A. They are positively charged and 3+. But if positively charged ions cluster on the left side, then it makes sense that negatively charged anions are found on the right side of the table. And here the numbering system works backwards. So in the US system, group 7A, fluorine, chlorine, bromine, and iodine, they're all -1. Group 6A, oxygen, sulfur, selenium, tellurium, they're all 2-. And group 5A, which includes nitrogen, phosphorus, and arsenic, they're all 3-. So what happens, though, to the atomic radius, and how does this charge tend to affect the size? Well, at first, if you're looking at the trend in the group going from top to bottom, the trend within the ionic radius within the group going top to bottom is exactly the same as the atomic radius. As the atomic number gets bigger, the size of the ion gets bigger, just like the size of a neutral atom gets bigger. But, and you can see this more carefully laid out in page 146 of your textbook, within periods the pattern is different. Cations are smaller than their neutral atoms and anions are larger than their counterparts. So right here we're showing purple circles to represent the positively charged cations and gold circles to represent some of the negatively charged anions. And these, shown on this slide, are the neutral atoms. But if we consider the ions, what do we observe? We should see that the atoms in purple are getting smaller. That is, their radii are decreasing. They are pulling in, whereas the gold-colored anions are getting larger. What's happening here? Well, when a cation is formed, there are more positive charges in the nucleus than negative charges in the outer shells. And so the positive charges pull more, and so the shells tend to pull in, and the atoms become smaller. But for the anions, which are negatively charged, the reverse is true. There are more negatively charged electrons in the outer shells than protons in the nucleus, and so they pull more. They pull more, and thus they become larger. So the overall pattern is that while size within groups going top to bottom increases, within periods both anions and cations tend to decrease with atomic number. And this is the reason why neutral atoms also decrease in size, because as you add electrons to the outer shells, they're pulling a little bit more, and so they tend to come together a little bit more because the number of protons and electrons is increasing at the same time, and they're both pulling on each other more. But the protons won't come out of the nucleus, and so it's only the electrons that are likely to move closer or farther away. Another trend of interest is what's called ionization energy, and this is the amount of energy that's required to remove an electron from an atom. Like if you wanted to steal an electron from sodium and take it away from sodium, you have to put in a little energy to take that electron out. So we're going to actually plot that trend on the periodic table, and we're interested in the question of, well, where's the highest and where's the lowest ionization energy? It turns out that helium, in the upper right-hand corner, has the highest ionization energy. It's a noble gas, it's very stable, it doesn't really want to give up any of its electrons, and so it really takes a huge amount of energy to take an electron out. Under normal circumstances, this doesn't happen. Again, the noble gases, group 8A, are inert. They tend not to do any chemical reactions with anything. So if helium is at the very top right, where would we find the item with the lowest ionization energy, which is just to say the easiest one to strip an electron from? Why, we'd find it in the far opposite corner with francium. Francium has the smallest ionization energy. To put it another way, this is something that increases as you go left to right, and it increases as you go up a group. Now, electron affinity, here with the symbol EA, is related to ionization energy. It is the amount of energy which is given off when an atom gains an electron. If you're gaining an electron, well, energy has to come out. So our example is if the neutral chlorine atoms are converted into chloride ions with a -1 charge, well, a certain amount of energy will have to come off in order for chlorine to add an electron to its outer shell. A price has to be paid. So electron affinity increases as you go up and to the right, just like ionization energy does. If we were to plot it as an equation, we would say chlorine plus electron leads to the chloride ion plus a release of energy. And it's not an accident that we choose chlorine to talk about, because chlorine has the highest electron affinity. It is a green, not odorless, and very poisonous gas. And you can actually see in the picture that the cloud of green gas slowly swirling inside the flask. And that is the element with the highest electron affinity. Now, electronegativity, which is really discussed in detail in the following chapter on page 174, electronegativity is kind of based on both ionization energy and electron affinity. And you can think of it as greed. You can think of electronegativity as greedy. How greedy are you to get an electron? It is the ability of an atom of a certain element to attract electrons to itself. We define it as the difference between ionization energy and electron affinity. We calculate it pretty simply, IE minus EA divided by 2. Fluorine is the most electronegative, which makes sense because it is at the top of group 7A, the halogens, which is the furthest to the right of any group which is not super stable, like the noble gases. Now, speaking of the noble gases, they are super stable. And so if we'll look on page 156 of our textbook, pondering the noble gases provides us with an important clue about how atoms want to behave. All of the elements of the periodic table desire stability. You'll notice desires in quotes. Now let me just be clear. When I say that an element desire or wants something, of course it's not alive, it's just matter. It's not a living thing with wants and desires. We're speaking metaphorically, but this is a convenient way to talk about what actually happens of how the laws of nature compel the elements to behave. And so the elements of the periodic table behave as if they desire stability. But some elements find it far easier to achieve this stability. Specifically, the noble gases. The elements of group 8A, the noble gases, are highly stable. And as mentioned, they rarely react to form bonds with other atoms. Why is that? We can get some clue by looking at this simple two-dimensional picture of the noble gas argon. The Bohr model of an argon atom clearly shows 18 electrons, and 8 of them are valence electrons. That is, the outer shell of argon is completely filled with 8 valence electrons. The same thing is true for all the noble gases. All of them have an outer shell that's completely filled. Helium has an outer shell that just has 2. But all the rest, neon, krypton, xenon, radon, all that, they also have outer shells that are completely filled with 8 electrons. If we look at it with the Lewis dot structure, we can see how this is symmetrical and balanced. Pairs of electrons arranged around the nucleus of the argon atom. And if we try to describe it in terms of the total number of electrons, we recognize that the last group at the highest energy level for argon, the third energy level, we have the 3s2 and we have the 3p6 orbitals, and the subscripts, when we add them together, 2 plus 6 is 8. And we can call this group of 8 that represents the filled outer shell an octet. This analysis shows that noble gases are uniquely stable and helps explain why other elements tend to adopt the electron configuration of a noble gas. As an example, let's consider cases where different elements have the same number of valence electrons. So if an atom of sodium loses its sole valence electron, it becomes a positively charged cation with more protons in its nucleus and electrons in its outer shell. Here, if we compare sodium, we can use both the Lewis dot structure and spin diagrams to see what's happening. Remember, the boxes in the spin diagram represent orbitals, regions of space around the nucleus of the atom of different shape and different amounts of energy, and each orbital can contain 2 electrons. Here, the electrons are represented by arrows in the opposite direction. You can have either 1 or 2 arrows in a box, so you can have 1 or 2 electrons in a particular orbital. Now, the first and second energy levels are completely full. There are 5 boxes total, all filled with 2 electrons for a total of 10 electrons. However, sodium's atomic number being 11, it needs 1 more electron. So it has to add a third energy level. And so sodium has a single orbital on its outer shell at the third energy level. It is the 3s orbital, and it has 1 arrow in the box because it has 1 electron. And we show that single valence electron in the Lewis dot structure is a single dot outside the symbol for sodium. However, there's room for as many as 8 electrons in the third energy level, and so that 1 electron, you might say, is lonely. And the forces tend to act to cause sodium to lose that valence electron. And you see that the box is now empty. And so this is no longer a sodium atom with an equal number of protons and electrons. It's a sodium ion with an overall charge of +1 because it has more protons in its nucleus than electrons in its outer shell. Let's now compare that with neon. The sodium ion in A plus has the same exact electron configuration as the noble gas neon. Neon's atomic number 10, and so it's perfectly happy to have 5 shells completely filled with 2 electrons apiece. And in the Lewis dot structure, we see the 8 dots symmetrically arranged around the element symbol, showing that it is both electrically balanced and structurally balanced, that it has an equal number of positive and negative charges, and it also has its outer shell completely filled. If we combine the fluoride ion F minus or the sodium ion in A plus, we see the same pattern. Both ions have 10 electrons, which is the same as the normal, electron configuration for standard, neutral, balanced, stable neon. Both fluorine and sodium are pursuing the same balance, the same arrangement that neon has automatically. Fluorine tries to get this balance by adding an electron to complete its outer shell. Neon doesn't have to do anything, it's already super balanced, super stable. And sodium, why its solution is the most radical, in order to get to 10 electrons, it actually loses its outer shell and the sole valence electron that it contains. Pretty radical. Notice that all 3 elements behave as if they want to have their outer shell completely filled with 8 electrons. Now don't get me wrong, these are different elements, and they do behave differently because after all, fluorine is negative and sodium is positive and neon is neutral. They behave very differently, but they also behave as if they're trying to be the same in terms of their outer shell. This tendency to have a filled shell of 8 electrons is called the octet rule. An octet is simply a group of 8. On page 157, we see a consequence of the octet rule. Group 1A, 2A, and 3A elements like magnesium, satisfy the octet rule by losing their outer shell, becoming positively charged cations. Groups 5A, 6A, and 7A elements, like chlorine, satisfy the octet rule by completing their outer shell, becoming negatively charged anions. It appears that atoms are caught in a tug of war between 2 competing desires. The example I like to use is that someone is in their bedroom and they are playing a video game online with friends, one of those massive multiplayer things where it just goes on, round after round, lots of mayhem, microphones, headphones, the whole bit. Well, imagine that someone is into one of those games and they're really intense and they really, want to continue for the whole game, and yet at the same time they're very hungry and they'd like to have a hot meal. Now, unless their bedroom is equipped with a microwave or a stove, they can't actually satisfy that desire by themselves and yet keep on playing the video game. They have to choose. They either have to say, sorry guys, I gotta go, I gotta eat, or they have to say to themselves, no, I'm really hungry and I want a hot meal, but gosh, this game, I gotta stay. But one has to make a choice if one is on one's own. So atoms, they have the same problem. They want to be structurally balanced, which is to say they want to have their outer shells filled. But they also behave as if they want to be electrically neutral. They would like to have an equal number of protons and electrons. But unless you're one of the noble gases in group 8A or a handful of other elements toward the center of the table, it's usually not possible to satisfy all these conditions at the same time. This is why most isolated atoms in nature tend to be ions with an overall charge. One way an atom can satisfy its desire to be both electrically neutral and structurally balanced is to share electrons with other atoms. Now, in the ionic bond, there's no sharing. One element gets its electrons stolen by the other, and the other is the thief. And which one is the thief is which one is most electronegative, the most greedy. So an ionic bond will produce ionic compounds held together by static charge, but it won't actually share anything. If you want to share an electron, that means that electron has to go around both atoms at the same time. An example of that is hydrogen. Hydrogen is element number 1, and a neutral hydrogen atom has 1 electron in its outer shell, and you can see that the Lewis dot structure for hydrogen is just 1 dot. But that hydrogen would like to complete its outer shell. and yet it also at the same time it wants to be electrically neutral. One way for hydrogen to solve that problem is to share its electron with another hydrogen that has the same predicament. And so you see in the drawing on the right, there are two hydrogen atoms there. They're both +1, and thus there's two positive charges, and there's a total of two electrons, two negative charges, but those two electrons are being shared by both hydrogens. In the Lewis dot structure, we put two dots in between the two hydrogens, or sometimes we just have a dash that means a pair of electrons being shared. The important thing is that in this situation, the hydrogen atom partners with another hydrogen atom to make a hydrogen molecule, which is diatomic. It's made of more than one atom. And so the covalent bond that's produced in this circumstance is very strong. We say covalent, that means it's sharing valence electrons. Like the word cooperate, it means we share. This sharing bond is 1,000,000 times greater than the ionic bond between charged particles. And it's the bond that makes really large molecules and complex structures possible. Now, as mentioned, hydrogen tends to partner with other hydrogens to form a diatomic molecule. And you need to know that in nature there are certain elements that tend to form covalent bonds with other atoms of the same element. You need to memorize them. There are a total of 7 such elements in the periodic table. We have hydrogen, nitrogen, oxygen, H2N2 and O2. And then we have 4 of the halogens: fluorine, chlorine, bromine, and iodine, which are, of course, F2, Cl2, Br2, and I2, respectively. All of them, except for hydrogen, are on the left side of the stair-step line, and thus nonmetals. Hydrogen is a special case. It's not really a metal in group 1A, but it is in group 1A. Notice also that hydrogen and fluorine, chlorine, bromine, and iodine, they all have a single line connecting them, so they share a single pair of electrons. But if we look at the top, at oxygen in red, look carefully, we'll see that there are 2 lines between the 2 oxygens. That's a double bond, which makes sense because each oxygen has 2 empty spaces it's trying to fill in its outer shell. And then next to that, we have nitrogen, 1, 2, 3, a triple bond. As a group 5A element, nitrogen has 5 filled spaces and 3 empty spaces that it would like to fill by sharing electrons. And that is not a double bond, that is a triple bond. And the triple bond, of course, is much stronger than the double bond, which is one of the reasons why that when we inhale the air, we get plenty of nitrogen, but it does nothing for us and it does nothing against us. We inhale it, about 70% of the atmosphere is nitrogen, and it goes into our bloodstream a little bit, it comes out of our bloodstream a little bit, but it doesn't do anything because the energy required to break that nitrogen that comes from the atmosphere and into, well, it's a lot greater than biological organisms are able to handle. If you did a chemical reaction strong enough to break that triple bond, you'd be setting yourself on fire. So good thing we don't. Now this is a lot of information, that there are 7 elements that you have to memorize. And so how are we going to remember this? That these particular 7 tend to be diatomic, because we have to keep track of this. A hydrogen atom behaves very differently from a stable H2 molecule. So here's our memory aid, developed by college students, used for decades with great success. Have no fear of ice cold beer. And that stands for respectively hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Now I want to be clear that if we say have no fear of ice cold beer, I'm simply giving this as a memory aid. I am not endorsing the use of alcoholic beverages. If one of your parents contact me and say, Mr. Hatfield, why is my child talking about beer in your class? I'm going to say it's just a memory aid. I'm not responsible for any choices. Though if I were responsible, a chemistry class is a perfect place to talk about the many different kinds of alcohols, which pretty much are all toxic, so exercise care. Okay, so those are the periodic trends. We compared them, and we'll come back and look at other trends as well, but that's a general treatment. There are certain properties like the atomic radius, ionization energy, electronegativity. They change from one part of the periodic table and to another. They change either going up and down in groups or left to right in periods. Why do they change? Largely, it's due to changes in the arrangement of the electrons in their outer shells. Now that we recognize these trends, we may be able to use the table to make predictions. Please recall from section 5.1 that one of the great advantages of Mendeleev's version of the periodic table is that he used it to predict the existence of elements that were not then known. That's very impressive. Hey, I can use this to predict something we didn't know. And he did, which is why that pretty much all periodic tables today are based in some way or another on Mendeleev's model. But if we go to page 138, we can also learn how to use a periodic table to make predictions. If we can remember that the periodic table is ranged in blocks like this, then it can help us make predictions. I ask you to visualize that different parts of the periodic table are based on those 4 distinct blocks, S, P, D, and F. And I remark that if you can remember this general pattern, it will help you remember the element's chemical properties, or how it is with those properties compared to other elements. Specifically, we're looking at the question of reactivity. Reactivity is the opposite of stability. If you're very stable, you don't react with other elements. You're highly reactive, well, you're very likely to react in certain ways. How will that happen? What should happen? Well, we can use a periodic table to predict this just by knowing where things are. For example, group 1A and group 2A cations come from the S block, and that means they tend to be highly reactive and form positively charged cations, whereas some of the other elements in the P block are either, like the noble gases, neutral, super stuck up, don't react at all, or like the halogens, group 7, highly reactive in a different way. We can remember this basic pattern, and we can remember basic trends of what's likely to happen in different parts of the periodic table, and so we can predict for an individual element how it will behave. And we can do this just by remembering a pattern. And thus you won't need to write out the full electron configuration and figure out precisely what every electron is doing at any given moment. Now, this makes it a valid distinction that we want to keep track of, a distinction between core and valence electrons. So again, if we're looking at sodium, we have a core, and the core is the first 2 energy levels shown in blue. The first energy level is small, there's only 1 orbital, it's completely filled, it's 1s2. The second energy level, shown in a darker blue, it contains a total of 4 orbitals, 1 s orbital and 3 p orbitals, and they're completely filled, 2 plus 6 for a total of 8 electrons. So the core for sodium is those first 2 energy levels in electrons. And as previously mentioned, that core, those 10 electrons, that's exactly the same thing as the electron configuration of the previous element, neon. And so we can use the noble gas configuration. We can actually write the symbol for neon in brackets. And then after that symbol, we can write just the electron configuration of the outer shell, shown in yellow. Sodium has to add 1 more shell to have that 1 extra electron to balance that 11th proton in its nucleus, and so it does so. It's 3s1. It's the 3rd energy level, it's the S shell, and it's partly filled with 1 electron. And so this is a nice, neat way to characterize things. Instead of writing out the full electron configuration, we can use the previous noble gas to describe the core electrons that that particular element will have, and then we just specify what's going on in the outer shell with the valence electrons. Now, where electrons are concerned, the way the core electrons and the valence electrons behave differs, and this is related to an idea called Coulomb's law. Coulomb's law says that the strength of the force between 2 charged particles depends on the charge of the particles and the distance between them. Well, an electron and a proton have charges. So here we have opposite charges attract. Of course, the pink circle with the plus sign represents the proton in the nucleus, and the green circle with the minus sign represents an electron in the outer shell. They have opposite charges, and so they are attracted to each other, so we have arrows pointing in. Yes, opposite charges attract. And the more charge, the more attraction. You have 10 protons in your nucleus, you have a little bit more pull than if you had, 9 protons in your nucleus. And so increasing the amount of charge increases the force of attraction. The arrows get bigger. But the further away you are from each other, the less you feel that pull. Distance decreases the force of attraction. And this can all be seen on page 140. Now I want to show you just a little bit more detail here on Coulomb's law, because Coulomb's law has an interesting structure. Don't freak out. You're not going to be asked to do this particular math, but I want you to notice that we do have an equation that describes this relationship, and it says F equals K, Q1, Q2, divided by R squared. Well, F is the force of attraction. It could be a force of repulsion. If you have like charges, they want to go in opposite directions, or it could be a force of attraction. If you have opposite charges, they want to come together. But it's a force that tends to accelerate them towards one another. And that force is equal to the product of the two charges, Q1 times Q2. The whole thing's divided by R squared, which is the distance. You take the square of the distance. And then we just add K. K is just a number that's thrown in there so that your answer is equal to a particular metric unit, the Newton. Now I'm just showing this to you so you can kind of see how this works, but I also want to tell you that there's an interesting mystery here. This equation for electrostatic attraction has the exact same structure as the equation for gravity. If we had Q stand for masses instead of charges, and then R squared is still the distance of separation, we can come up with a version of this equation that gives you an answer in newtons, only instead of electrical force, it's talking about gravitational force. The fact that gravity and electromagnetism have equations that have the same structure that you can substitute for each other is interesting. We don't know if it's due to a coincidence or if it has some deep meaning as to in terms of how the rules of the universe are put together. But I wanted to show that to you and see if I could provoke some deeper thinking. Now, the fact that the core and the valence electrons are all negatively charged leads to some interesting effects. And so on page 141, we're going to talk about the shielding effect and the effective nuclear charge, often represented with Z sub F. So negatively charged electrons are attracted to the nucleus because, again, opposite charges attract. But the core electrons are closer to the nucleus, and so since they're closer, they experience a greater force of attraction. R squared for them is smaller than it is for the valence electrons. Now, the valence electrons are attracted to the nucleus as well, but they're not attracted as much. And also, they are repelled by the core electrons. That is, the negatively charged force field of the core electron is between the valence electron and the neutrons. And as the valence electrons approach the core electrons, they're both negatively charged, and so they tend to repel each other. And so for this reason, the valence electrons are not held anywhere nearly as tightly as the core electrons. And we talk about the effective nuclear charge, which is the actual strength by which they're held. This is very easy to calculate, as you can see on page 142. If Z is simply the number of positive charges in the nucleus and S is the number of negative charges in the core electrons, then the effective nuclear charge is Z minus S. So in the case of sodium, sodium has 11 protons in its nucleus, but it has 10 core electrons. So the difference between them, 11 minus 10, is plus 1. Magnesium, the difference is 12 minus 10, plus 2. Aluminum, the difference is 13 minus 10, plus 3. It's always 10 because all three of these cations follow the octet rule, and when they become ions, they tend to lose their outer shell, and they keep their core electrons. And so the difference between the two is 1, 2, and 3, respectively. Thus, ions tend to have charges which are consistent with what is predicted by the effective nuclear charge, Z sub F. And again, this leads to certain properties, as seen on page 160. Again, we have sodium ions shown in gold and chloride ions shown in green, and they have opposite charges, and that causes them to come together. And again, when they come together, that leads to the formation of ionic compounds. And these are substances that contain two or more atoms held together by the difference in charge. In effect, static electricity. In our next set of notes, we're going to look very carefully at ionic compounds and how they're formed and how they observe the octet rule. And particularly, we're going to learn how to name them. There are rules for naming ionic compounds, and there are rules that allow us to predict in advance what their structure must be. How many of the positively charged cations we need, how many of the negatively charged cations we need. And so we will have an assignment worth a great deal of points where you'll be asked to rehearse that skill of predicting the formulas and naming ionic compounds until all of us can do it pretty much